All right, hello calculus students. In this video, we're going to investigate the interval of convergence for the natural log function, or for the Taylor series for the natural log function centered at x equal to 1. Before you watch this video, please make sure that you have read the Google Doc that accompanies section 6.8, as it does a nice job of outlining the intuition behind the ratio test and this whole notion of interval of convergence. So you're looking right now at my computer screen, and we see the natural log function graphed in orange, and then I believe 44 terms in the Taylor series for the natural log function centered at x equal to 1. That polynomial is graphed in green, and we can see that the green function and the orange function don't line up for all values of x, and it appears that they only do so for values of x between 0 and 2. And the goal right now is to figure out an algebraic or an analytic process for confirming what it is that we're seeing now on Desmos. So I'm going to go up to the whiteboard and give me 1 second to mount my phone. And here we go. So a reminder on the board of what the Taylor series is for the natural log of x centered at x equal to 1. And the goal of the ratio test for convergence is to figure out as n approaches infinity. In other words, as I look at terms way out in the Taylor series, is the ratio of consecutive terms such that the series is behaving like a convergent geometric series. In other words, if I take the ratio of two consecutive terms way out in the long list of terms, does that ratio have an absolute value less than 1? And if it does, then we know that the series will converge because it's behaving like a convergent geometric series. So what we're going to do is we're going to investigate the limit as n approaches infinity of the absolute value of the n plus first term over the nth term. Okay, this notation looks a lot more intimidating than it actually is. All that is doing is putting two terms that are next to each other in a ratio together, and what we're looking at are terms way out at infinity. And so we have our general term right here. And so to figure out the n plus first term, all we need to do is plug in n plus 1 wherever we see n. I also want to point out for this particular series, it's an alternating series, right? We have that negative 1 to the n minus 1, making the series go positive, negative, positive, negative. We're only concerned with the absolute value of the ratio of consecutive terms, so which will always be positive. So we actually don't even need to, we can neglect working with the negative 1 to the n minus 1 in our algebra, which is a little bit nice. So let's look at what this ratio becomes. So we have the limit as n goes to infinity of the absolute value of the n plus first term would be x minus 1 to the n plus 1 over n plus 1. And that's going to get divided by the nth term. So all of that gets divided by, and I extend my absolute value bars, the n plus first term, which is x minus 1 to the n over n. Okay. And again, just a quick reminder that I'm not including the negative 1 to the n minus 1 in my work, because that's just affecting the sign of the terms. And if we're taking the absolute value of the ratio of those two terms, and the ratio of the terms would be negative since it's alternating positive, negative, positive, negative, the absolute value though would still be positive. And so this becomes the limit as n goes to infinity of, we're going to write this, be a little bit cramped, but x minus 1 to the n plus 1 over n plus 1 multiplied by, when I divide by a fraction, I multiply by the reciprocal, which would be n over x minus 1 to the n. And now, to finish out this limit, we need to manipulate the expression that we currently have. So I'm going to continue that over here. So I've got the limit as n goes to infinity of the absolute value of, I'm just going to use the commutative property of multiplication in the denominator to rewrite that as x minus 1 to the n plus 1 times n over x minus 1 to the n times n plus 1. Okay, and now we're going to simplify this to our liking. We have the limit as n goes to infinity. X minus 1 to the n plus 1 over x minus 1 to the n just becomes x minus 1 multiplied by n over n plus 1. Okay, we're getting there. Now we're going to use a property of limits, that the limit of a product is the product of the limits. So we have the limit as n goes to infinity of the absolute value of n, x minus 1 multiplied by the limit as n goes to infinity of n over n plus 1. Okay, and so now we just have to investigate these two limits. The limit as n goes to infinity of n over n plus 1, just plug in a really big number, convince yourself that that's pretty easily the number 1. And then this limit over here, there's no n to plug into, right? So that x would really just act as a constant, whatever x we plugged in to our given series, we would just get that back. The limit of a constant is a constant. And so what this limit reduces to is the absolute value of x minus 1 times 1, which is just the absolute value of x minus 1. And after all of that algebra, it's easy to get lost in the weeds and forget what you were even, like why you were even doing all of that. And remember, all that this expression represents, this absolute value of, oops, just got this whiteboard. Okay, I'm not gonna redo the video. So I was so excited about this whiteboard, so, but apparently forgot to fully unwrap it. So we had x minus the absolute value of x minus 1 times 1 is equal to the absolute value of x minus 1. My apologies for not having fully prepared for this video and for dragging it out even longer, but what that represented, going back to the beginning of the problem, was the ratio of consecutive terms way out toward or at infinity. So in that long Taylor series that we have, what that work just said is that if I put two consecutive terms in a ratio with each other, the value of that ratio for terms way out toward infinity will be given by the expression the absolute value of x minus 1. And we want that to be less than 1. Because if that ratio is less than 1, then that series is behaving like a geometric series that converges because the ratio of consecutive terms has an absolute value that is less than 1. And so here's where we have a little bit of power. And the first time I've done it. And now we simply need to say, if this expression, right, is our ratio of consecutive terms, in order for the series to converge, we need that ratio to be less than 1. And so all that means is that x minus 1 has to fall between -1 and 1. And if I add 1 here, here, and here, I get that 0 is less than x, which is less than 2. Which, if you recall at the beginning of the video, we had already kind of had some visual evidence that the Taylor series for the natural log function centered at x equal to 1 had an interval of convergence, or the function and the series kind of laid on top of each other for values of x that were between 0 and 2. And so the final thing that we need to do. The only thing that the ratio test doesn't help us with is it doesn't tell us whether or not the Taylor series converges at these endpoints. So we actually have to go back to the Taylor series for the natural log function and plug in these endpoint values to check for convergence there. And so if you recall, our Taylor series for the natural log function is given by this sigma notation. And so the first thing that we're going to do is we're going to plug in x equal to 0, which, if you think about it, the natural log function isn't defined at 0, so I don't anticipate that there will be convergence when we plug 0 into this infinite series, and we can confirm that pretty quickly. So if I have the series from 1 to infinity of -1 to the n minus 1 multiplied by, if I plug in 0, I'm going to get 0 minus 1. I'm actually going to show that to the n, all over n. And then this becomes the series from 1 to infinity. Let's see, that's -1 to the n, and that's -1 to the n minus 1. So I know I can just add those two together to get -1 to the, I can add the exponents because I'm multiplying terms with the same base. Be precise in my mathematical vocab. So I've got -1 to the 2n minus 1 all over n. And if I think about it, if I just had -1 to the 2n, that would always be a positive 1, right? No matter what n is, I'd always have a positive number if I multiplied n by 2, or excuse me, an even number if I multiplied n by 2, and -1 to an even number would be a positive 1. Therefore, if I subtract 1 here, I'm going to have -1, right, to an even minus 1. An even number minus 1 will always be odd. So -1 to a number that's always odd will always be -1, which means that we have the series from 1 to infinity of -1 over n. And if you recall your work earlier with the harmonic series, this is just a multiple of that harmonic series, right? It's just a harmonic series multiplied by -1, and we know that the harmonic series diverges. So we know that we're going to diverge at x equal to 0. And now, final step in this process, it is a long process, so thank you for sticking with me for those of you that are still watching. I've got -1 to the n minus 1 times, right, now we're plugging in x equal to 2, the other endpoint. And when I plug in x equal to 2 here, I get -1 to the n minus 1 multiplied by 2 minus 1 to the n over n. So that becomes the series from 1 to infinity of -1 to the n minus 1. Let's see, 2 minus 1 is 1. 1 to the n is always going to be 1 over n. And so now we want to think about this series right here that results from plugging in x equal to 2. And we know that this -1 to the n minus 1 over n is the alternating harmonic series. And the cool thing about the alternating harmonic series is that it converges. So that converges by the alternating series test. Go back to the previous section or Google a video on the alternating series test to investigate why, or just look up the alternating harmonic series. And so what we have finally concluded is that the interval of convergence for the natural log of x Taylor series at x equal to 1 is all values of x between 0 non-inclusive and 2 inclusive. And that is the process for finding the interval of convergence. I'm going to do a couple more examples, so look out for those, and thanks for watching.